Hi everybody, I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University. And now we're back to the fifth and final part of our lecture on LVS. We still have another part which is DRC and chip finishing, but this is our fifth and final part about LVS within the digital on top physical verification lecture. Okay, so we discussed the basic introduction, which is the overview of how the LVS flow runs. Then we described how we get our netlist in Verilog out of the place and route tool. We ran v2LVS to provide our source netlist. Now we ran extraction and we have our layout netlist. So we have both the source and layout, and now we can go into actually running LVS comparison. So now that we have both the source and the layout netlist, we can use Calibre to run the comparison. And remember, what we're doing is we're taking the source netlist and layout netlist. These are both SPICE netlists, and we're going to now compare the two of them. This, again, can be done with Calibre, with all kinds of options to make it go fast, and then we just give a path to the run set. I already want to tell you that we can give a run set that does both extraction and comparison in one shot. The reason I showed it in 2 steps is because it's actually doing 2 separate types of things, and we can debug things by doing the extraction separately from the comparison. But once you have a flow that's running well, you can just give one type of a run set file, and it will run extraction and comparison in one single run. Okay, so again, we have a run set file that tells the tool how to run the comparison, and this includes now the paths to the 2 netlists. Before, in extraction, we just had to give it the path to the GDS. Now we have to give it both to the source netlist and the layout netlist. So how we do it is with layout path and source path. So the layout path will point to the layout netlist. The source path will point to the source netlist. They both have the same top level name, and they're both in SPICE. Now, if we wanted to have it run in one shot again, do extraction and comparison together, we would have had layout system GDS and point to the GDS instead of to the layout netlist, and then it will run extraction. It will dump the layout netlist, and it will run comparison immediately after it. So, what are the principles of LVS? Before trying to understand what's wrong, and there's going to be stuff that's going to be wrong, and it's going to be really hard to debug. Hopefully, a lot of the stuff that I've showed you before will eliminate many of those problems. But still, you're going to probably have all kinds of things that will go wrong, and you're going to have to try and debug and find out what's going on. So let's try and understand the basic mechanics of source versus layout comparison to try and understand what's going on. First of all, LVS is a type of a formal verification. In other words, it's black or white. The 2 netlists are either equivalent or they're not equivalent. There's no middle ground. This makes it really hard to debug. In other words, if the source and layout netlists are the same, everything is good. We're going to get a nice smiley face at the end of the thing. A lot of these LVS tools, they tend to put out a nice little smiley, or it'll just say correct, but sometimes they put out an ASCII type of a smiley, and then everything is good. Maybe it's just going to be like a check. Okay, and that's what we want. But if there's even one tiny thing wrong, we're going to get an X. And with an X, it's going to give us a type of a guess what's going on, but it may not have anything to do with what's really wrong, because it's really a formal verification, and if some small thing is wrong, it's just incorrect. Okay. That being said, the anchors to starting the whole thing are the top level ports. Okay. The comparison is told by us that the port X in the source is port X in the layout. So we're going to actually have our source and our layout. We're going to give top level names. We're going to say this port is X or whatever, in 1 or in 2 or whatever, and in the layout it's over here. That's where it starts. That's our ground truth. LVS starts from there. It assumes that that's true, and if it's not true, then nothing's going to work. That also means that there has to be the same number of ports with the exact same names in both the source and the layout. If that is not correct, that's the place to stop and go and fix it, because it's something that we really defined as the ground truth. It means that there's something wrong in our port definition, and let's start over. If the design is not equivalent, the tool tries to give a best guess. So we said before that there's no middle ground, but the tool wants to help us debug, so it's going to invent this type of a middle ground. Okay, it makes a guess. Unfortunately, the guess is not always that great. Sometimes what it puts out is just complete chaos. Okay, but it usually includes many different hints that can point us to fundamental problems, and we'll use this in a few seconds to actually try and debug our LVS problems. So let's look at the LVS results database. The LVS results database is usually dumped into a folder called SVDB by Calibre. That's the verification database. Okay, and you can open it using a tool called Calibre RVE. That's the results viewer from Calibre. So Calibre -RVE SVDB will open this results viewer. But one of the things is we don't get connectivity to the layout. If we want to have like be able to right click and say highlight, and it will zoom into our layout at the place where it thinks the problem is, we're going to have some sort of connectivity to the layout. So if we use the Virtuoso layout editor, we have a Calibre plugin, and we can run start RVE from there. We can also run from this same place. We can run DRC, LVS, and so forth from this type of a menu. Okay, and then I'll do the same thing. But anyway, what I really often do is I script my whole run. So I have my SVDB folder there, but then I open up Virtuoso, I open up my layout, and I start RVE and open up the results browser to debug it from this type of viewer. That opens up RVE. RVE enables us to choose what type of a database we want, and in this case we want the LVS database. So we click on that and then open up the SVDB folder and click open, and it will open up our results browser. This, if we run it from the run LVS over here, run nmlvs, it will open automatically the RVE on the results database that comes out. This will also show us the ERC results, so they're also saved in the same SVDB database. So we didn't discuss it before too much, so I'm going to discuss ERC database now. So what is ERC database? That's the electronic rules check. Sometimes guys who are doing layout look at that and say, what is this ERC? Why is it complaining, and so forth? So I'll just give you some intuition. I can't go into many of the different things. There are thousands of pages of manuals that discuss this, but you should start by at least looking at it and trying to figure out what it's telling you. So ERC is run during the extraction stage, but you can view the results along with the comparison to database results. It's inside that same SVDB folder. Okay, ERC checks tell you about things like short circuits, open circuits, and problems with bulk connections. Remember, it's run only upon the layout. It's not run as part of the comparison. So it's not comparing the layout to the source and telling you what the ERC problems is. It's just running on the layout. So stamping conflicts, for example, as I told you before, is if we have two different nets that are connected physically inside the layout, but they have different names. And remember, the names are our golden rule. They're our ground truth. So we said that this is net A and this is net B, but it sees that they're actually shorted together. It says, listen, there's a short circuit between net A and net B, and that's a stamping conflict. And it's also true if we have two nets called VDD and we don't do this virtual connection type of thing. So it says this is called VDD and this is called VDD. Well, I don't realize that VDD and VDD are the same because there should only be one, or else they're not actually shorted together, and it says there's a stamping conflict between them. So what do? Again, we open this RVE, and we have our extraction of the ERC results here. Here they're shown without LVS results, and we can see that if we go to our top level, there's a stamping conflict here, and it says in this case that NetVSS has a stamping conflict with these two other VSSs, and indeed in this design they were shorted together through the bulk, so it's a real actual short circuit that it found. Okay, sometimes, especially in hierarchical blocks, maybe in some memories you got from a compiler or something, you will have stamping conflicts in lower levels, and if it passes LVS, I guess these things can be ignored. You should check with your vendor, check in the manuals if something appears, and so forth. But there can be these types of stamping conflicts in lower level blocks. Okay, after we checked that was the log file basically. So this was viewing the log file. We should also check the ERC report, and there are different parts of the ERC report. Okay, there's a soft check database and the ERC results, and they have different types of things, like they check the substrates that they're connected and so forth, and you should really go into here and check what they are. If you click on one of these errors with a right click and highlight, or just press Shift H, it will actually zoom in to the area on your layout and put a marker on the layout of what it sees, and that can often highlight all kinds of errors. So you want to try and fix these types of things. This is not a gating LVS, so you can pass LVS despite having some ERC problems, but you should really understand what they are and see that they're fake problems and not something real. Okay, so now that we got past ERC, we're going to look at the comparison results. And again, it's looking at the same type of a database, but we need to know some debugging principles. Now, I can't give you much more than just tips of things that I've ran into, because this is really kind of like an escape room. You have these problems, you have to find out what they are. You don't know how long it's going to take you, if you're even going to find the problem. Eventually you should find the problem, because you know that the source and layout should be equivalent, should be the same, and assuming that the place and route tools are doing their job, then really it should work in the end. But it's really a hard riddle or a hard quiz type of a thing to find the solution. It's a tough puzzle. Okay, so some principles about it. So as I said, port comparison. If your ports are not equivalent, don't look any further. Go fix the ports. As I said, these are the staples. These are the anchors of our LVS. If the ports aren't equivalent, don't even start because nothing else is going to work. Hierarchy comparison. Well, make sure lower level hierarchies pass LVS and ERC, and make sure the connections to these hierarchies are correct. I'll discuss that in a minute, but obviously every block that you should get should be able to pass LVS and ERC standalone. Bulk connections. So the bulks are pretty clear, usually VSS for NMOSes and VDD for PMOSes, but sometimes that doesn't happen. So if some transistor in one of the netlists is connected to something else, that is probably a good place to start looking for problems, and I'll show you some examples in a minute. Okay, device connections. Well, as I said before, if you have an incorrect answer, it means that the source and layout are not equivalent, and then it will start trying to make some best guesses. And these best guesses are often, they don't tell us anything, but sometimes they do. So it'll usually try to match devices by their most equivalent pin connections. If 3 out of the 4 pins are connected correctly, try to look at the 4th pin because it must be something wrong there. So I'm going to start with the tips now, and here's tip number 2. Why am I starting with tip number 2? Because tip number 1 was to get your ports right. Remember, always get your ports right. Don't ever look forward if your ports aren't correctly right. So tip number 2 is H cells, and this is what I discussed before on hierarchical comparison. So to get this to run, we provide a file that's called H cells that details all the hierarchical blocks, soft hierarchies, and hard macros. And this is really important because it can really look at the LVS separately between what our bottom levels have problems and our top levels. So this is really a dumb file, stupid file, I would say. It's just the name of the block twice. My block 1, my block 1, my block 2, my block 2. This is the H cells file, okay? And when you run Calibre, you actually write -H cells and give it the name of the file that has this definition in it, okay? So if you do that, it can help you debug. It can help run LVS. Once we do that, what you'll see is that when we run LVS, you can see that each one of the hierarchies that we defined will get a comparison. And in this case, look, we got a smiley face at the end. So this was a good state. Each one of these hierarchical blocks that were defined in the H cells passed standalone, and the top level also passed. So if not, we'll have some sort of X's here or different things. And we can also do things like boxing and filtering, which we'll see in a second. Why would we have problems here? Well, one, if of course our lower level provider didn't pass LVS, but that we shouldn't even start with. But another thing is it might be that there's some problem with connectivity between the top level and lower levels, and that at least points to us to a place where we should look for problems. Okay, so that's why H cells helps. If we see that one of these is an X, even though we know it passed standalone LVS, we should look at the interface between them, how we can actually go into the layout, look at the layout, see if things are wrong, as we'll be discussing in a second. Okay, excludes, filters, and black boxes. So there are 3 words, 3 commands inside the SVRF language: exclude, filter, and box. And they can help us remove a block for our comparison. The first thing is if a block is not quite ready, so we started running LVS when one of the blocks wasn't made yet, we don't have a GDS, whatever, so we can exclude it from the comparison. Okay, maybe we don't want to have it run on it because maybe there's some sort of problem inside, we can black box it. Okay, and so this can help us debug, especially when we get those H cell LVS errors. Okay, and sometimes we don't have the GDS or CDL of a block. This often happens for instance, in universities. We get libraries that don't have the back-end views, so we have to black box our IPs, or else we can't even run LVS. Okay, so to understand the differences, you should read the Calibre manual, but the syntax is basically like this. If we want to exclude, we do something like LVS spice exclude cell layout and my missing block. It should remove it from the extracted netlist. Okay, LVS filter my problematic block open both. We can use open or short here. It will filter a certain block, and it will either cause all the pins to be open circuits or short between them. And LVS box my problematic block will basically cause this to be a black box. Will connect the pin connectivity, but won't dive down inside the block itself. Tip number 4 is bulk connections. So a good place to search for problems is in the bulk connections. Okay, if you start by running DRC, which I'm showing in the second part of this, or actually the sixth part of this lecture, this will highlight these things. You should actually run DRC first. I just started with LVS because it's much more interesting and complex and so forth. So if you run DRC on your block that comes out, you can get a lot of unexpected errors that are highlighted, such as NWell overlaps, missing well taps, and all kinds of other things. So if you check DRC, and for example, we could have a problem such as this. Let's say this was our top level, and we had all kinds of standard cell rows here, and we cut them off, and we had some sort of a hard macro over here. But for some reason, this standard cell row actually went into the hard macro, and then we had a cell here on top of what was going on here. We'll have all kinds of problems, even if they're fillers or whatever. We may have all kinds of bulk connection problems, and we'll probably, when we highlight all of these errors, we'll see this big number of X's, big number of highlights over here. So we should then go in and look in, and we can see that our left wasn't defined correctly, and that's why we had these types of overlaps. So that's kind of a thing to see, and it usually comes out when we look at DRC. We'll have all kinds of problems in this area. So that can really, anything like this will cause LVS to completely break, but DRC will immediately highlight it as a problem, and you can go and fix it. Okay, the next step is going to the ERC reports. So if there are warnings about short circuit, stamping conflicts on VDD and ground, check the soft connect errors and highlight to see which connections is wrong. What if we forgot to put in all kinds of fillers or all kinds of different well taps and so forth? They'll be shown inside the ERC report. Has nothing to do with comparison. It's already in the extraction. And finally, we can take the LVS, but again, that's comparing the source to layout, and that's a much later stage. If we get to there, we're going to be scratching our head. It might be a problem, but we can look at the device connections in the LVS report. If we see in the device connections that our bulks are not connected to VDD or ground, that's a good place to start looking. For example, if the bulk is connected to net 1, 2, 3, 4 or something else, we have to understand why, because we don't know a certain transistor what should be connected to the gate, source, or drain, but we do know that the bulk should probably be connected to VDD or ground or some other power or ground rail. Examples of things that can cause problems with bulk connections, and we have a chip called Leo1, which I've been showing in the examples here, and we had all these things happen. We forgot to add fillers in certain places. Fillers were added where they weren't supposed to be in other places. We forgot to add well taps, or the wrong well tap cell was used. We wrongly connected the well taps. Okay, we had overlaps between macros, and all those things can cause you bulk connection problems. Tip number 5, device connections. Okay. The last very weak general tip I can give is to look at the detailed instance info section of RV, and that's also what I said before when we were debugging bulk connections. Sometimes you can tell by the names of the nets that something is connected wrong, such as a flip bus or something, but in general, this is when you really start to scratch your head and have problems. So if we look at the comparison report and we see that it has a frowning face, the yellow frowning face, we look at the thing and you see that they're incorrect nets, incorrect instances, property errors, and there are lots of them. In fact, this is the maximum that we allowed inside the LVS run file. Okay, and it's going to be really hard to look at. So we should look at the detailed instance info, and we should look at the bulk. You see that the bulk over here is connected to VSS, and over here, if we can find some instances where they're actually not connected, that can point out something. But we can also look at the different names of the nets and see maybe something like flip bus or other types of things. But this is really hard. This is where the puzzle really starts in the escape room type of mentality, where we have to find our way out of this and we don't exactly know where to start. So that's what I have to say about running LVS, and now I'll show you some things on a real design. So we're finally at the point where we can run comparison, LVS comparison between our two blocks. But before we start, I just wanted to show you the HCell file. So it's a kind of a stupid file that all it has is the name of a module, the name of a block, space, and its name again. So we write the name twice, and this will cause it to run the comparison in a hierarchical fashion where we can separate the run on each one of these blocks separately. Okay, so that being said, I want to also look at the comparison script, the run set file, and here again we have the layout path and the source path, and because I decided to do it in 2 steps and do extraction and then do comparison separately, so they're both pointing at SPICE files where we have we're pointing to the wrappers that I showed you before. They're going to be the 2 things that I'm going to compare. Okay, as I mentioned also before, we can do things like exclude or box or filter. Usually at this point we'd be using box or a filter command if we want to get rid of one of our hierarchies or one of the maybe hard macros that's not ready yet or something like that. Or in case we don't have backend views, for example, we'd want to box it. Okay, basically we have all kinds of options here, like what our maximum number of errors are that we report and so forth inside here. And finally, again, it's going to call the rule file from the Foundry. Okay, so now that we've done that, we can go and we can run our Calibre command. Again, it's going to add the H cells and it's going to run the compare, that compare script we looked at. And now it's going to just run for a while, and while it runs we can go and have a cup of coffee or something, because this can take a while depending on how many machines we have, depending how complex our design is, how many errors there are, and so forth. And indeed we have LVS completed and we get this thing that says correct, which means we're very, very happy. Okay. Now that we got that, we can go over to our layout. We can go Calibre, start RVE. Okay, we don't actually need to do it now because LVS came out correct, but if it hadn't come out correct, we select LVS over here, we select SVDB, and we open it, and we should have a nice smiley face which will make us happy. We ran it on the wrapper. So when we open the wrapper, we get comparison result is a green smiley. And because we had H cells on, we have each of these different levels is an H cell. And finally, we got Leo1 top wrapper, which is our top level, which is correct. We get this nice V and this nice smiley face, and it says that everything is okay. So that's what we wanted to do. So I can only wish you to have many of these little smiley faces in life in general, and especially when you're running LVS. So that's it for the part about LVS in this lecture.